Well, good morning. I can guarantee you this presentation will not be as entertaining as Jerry's, but I will try to take his advice and live in the moment and enjoy the next 20 minutes. I'm Arlen Martin. I'm with Reflex Photonics. Reflex is based in Montreal, Quebec. I joined the company as marketing director in November. In the same month, the company was acquired by Smith's Interconnect. So there's a lot of good changes happening at Reflex. So the title of the presentation is Blind Made Optical Transceivers for the VPX Backplane. There's been a lot of work over the last number of years more than a decade, to implement standards for optics in the backplane. And a lot of that is now being driven by the VITA organization. A lot of work is being done here. Michel Tattoo is here with us today as well from Reflex. He is our representative in the standards. He's been doing a great work with the VITA organization to do this. So why do we need to go to optics in the backplane? The challenge with the electrical signaling is having good signal integrity on the boards as we get to higher speeds. So as we're moving to 10 gig, actually at 10 gig and moving towards 25 gig, it's very difficult to move those signals at that rate on copper traces on the board. At the bottom, there's a differential pair of traces that is about 10 centimeters or about 4 inches. So on the right here are the challenges of dealing with the electrical signals. And you have to be very careful in laying out the traces to maintain the signal integrity, but you've got issues with reflections and losses and crosstalk. The designer has to be very careful in how the traces are laid out on the board, the material choices, and you're very limited in the distance you can go, as I said, about 4 inches. So there's a clear path to move to the optical transceivers to do this. There's also an advantage in the power consumption moving to the optical side, because as you deal with these electrical signals at high speed, you have to do a lot of work to maintain the eye opening with methods like equalization, pre-emphasis on the signals, and that drives the power consumption up of the solution. So when you move to optics, now if you look at the bottom on the path, the optical path, you can go up to 300 meters on multi-mode fiber. And so you eliminate that distance challenge. When you look at signals that are being generated by devices today, and the example here is the Xilinx Vertex UltraScale Plus, that device has 128 ports on, each able to handle 32.75 gigabits per second. So there's a tremendous amount of data that can be passed around inside a VPX chassis. And so that's the main driver behind going to the optics. When we look at the optical modules, you have 3 choices of where to place it on the plug-in card. First being at the back edge of the plug-in card, where it will mate directly to the backplane. You can put it midboard anywhere in the space of that card. The third option is on the front panel at the bulkhead. And there, you're very familiar with these. These transceivers have been around for more than 2 decades. With the SFP transceivers, today the QSFP transceivers are commonly used for these higher data rates. I won't be talking about the front panel. Mainly, we will just look at the 2 other options, the midboard and the board edge. Each of these have their own advantages and disadvantages, which we'll look at. But first, if we look at the apertures that are required in the backplane, these are defined in the proposed ANSI VITA 65 standard. There are 4 types. If you start on the right side, this is the half-width opening. Both of these are half-width openings as defined in 66.1 and 66.3. These are defined in the VITA 67 standard. All of these can be populated with either optical or RF connectors. The smaller versions that you see on the right are half-width. This is a full width, and this is a full width plus half-width. On the bottom left, you see an example of a backplane card from Elma. And you can see the slots for the backplane. On the left, you see one half-width connector. This is a MT optical connector. Next, you have 2 full-width openings in the aperture for a MT connector for optical, along with RF connectors for electrical signals. And there are some more examples. And here is a full and a half-width opening in the aperture. Backplane positions are defined as from J0 to J6. This is on a 6U slot. The same can be said of the 3U card, where there are 2 openings here. But if you look at these 2 openings, for example, the J3A and J3B, if you put the optical modules in there, the MT connectors will be spaced on a 14.4 millimeter pitch. And so the density is high for the amount of transceivers that you can put into the optical backplane there. So let's look at those 2 design options of mounting the transceiver midboard and at the back edge of the card. In the first example at the top here, you can see that the optical module is mounted at very close to the signal generator, or an ASIC or an FPGA. That gives you the advantage of shortening those electrical traces, and so you minimize the challenges of your electrical layout. But now you have to move the signal through an optical fiber to the back of the card to a floating head optical connector. And I'll talk more about the floating head and fixed heads in a minute. But you have to have an optical connector on the back of the board to mate to the optical connector on the backplane itself. So this gives you the advantage of putting the optical transceiver very close to the signal generating chip, but it takes more board space. The second option is to put the optical transceiver at the back of the board, and we will integrate the fixed head optical connector to the transceiver and move the floating head to the backplane connector. Now we're only taking up one area of space on the board compared to the first solution. It does have the disadvantage of having a longer distance from the signal generating chip to the optical transceiver, but it's minimized. It's going to be less than 4 inches, and so that is manageable. So those are the 2 options to minimize, or the trade-offs between minimizing the board space and the signal distance. The standard also has the ability to put passive fiber optic connectors in the system, and here's an example of a TE card. Here are 2 half-width modules. You can see the fiber cable coming in. No active opto. This is just a straight pass-through of the optical signal to the backplane. So the 2 half-width modules with MT connectors, and here is a full-width connector with 2 MT connectors. This gives us the ability to scale dramatically with the optical transceivers, and there's future expansion because these MT connector systems can be increased to 72 fibers per connector. This is the view of the active connector system. And I said there is the fixed head and the floating head part of the connector system. The floating head allows this MT, here's the MT connector, it allows it to float a short distance in both the X and Y direction. So as the backplane card is the card is being inserted into the chassis, to the backplane, that initial alignment has some float to get the connector system to align properly. The card is inserted in the direction of the green arrow, and that gives the mating force. The primary guide does the initial alignment, and then these dowel pins in the MT ferrule, they do the final precision alignment of the 2 MT ferrules to bring the fibers within plus or minus 5 microns of alignment. There is a spring in the floating head connector that provides the mating force between the 2 MT blocks. This is an example of some of the options for putting the transceivers into these applications. You can see there's a number of different versions. We have, both of these are the active optical modules with a single MT connector. This is the active optical module on the bottom with a passive feed-through of an optical signal on the top, just the cable coming to an MT connector. Next option is the active optical module with stacked RF connectors above it. So you have 8 RF connectors and an optical MT in one half-width slot. All of these are half-width, so they can go in any of those aperture openings that you saw. And then finally, the last one is stacked 2 active optical transceivers again. So these can be all mounted to the board with a screwed application through an electrical interposer. On the right, you see some examples of these modules. The top is showing a 12 transmit or 12 receivers in one module. And the bottom device is a 4X transceiver, so 4 lanes transceiver. This is a cross-section of the optical mating system. So on the left are the interposers, And you can see the interposer is this block right here. So the electrical path is coming from the plug-in card, as shown in red, through the interposer, into the module and the ICs in the optical module, to the VCSEL laser, which converts the signal to light, which is now on the blue path. The light goes through the MT ferrule of the transceiver, coupled to the MT ferrule of the floating head connector system. Here you see the spring, which maintains the force for mating the two MT ferrules, and out the other side of the backplane. So that is an overview of the connector system. Here are some examples shown on a backplane. You can start with the top and see that this is a single active optical module. There's one MT connector. Next is what we saw earlier with the optical MT and the stacked RF connectors. Both of these are half width. Then there's a full width populated with an active optical module and a passive feed through. And here is the card that plugs into this slot. So you see the active optical module here, the stacked passive feed through, and then there's an additional active optical module that mates to this MT ferrule on the backplane. And then finally on the bottom you see a half width with, again, the combo RF opto and a full width of the RF connector system. So all of these signals are coming to the backside of the chassis where they can be routed from one slot to any of the other slots. Where, as I said earlier, this now has the option, because of eliminating that distance challenge, of being able to take the signals directly out of the VPX chassis and routing it to another chassis somewhere, so you can interconnect chassis up to 300 meters apart. And so it enables a lot more ability than using the electrical signaling. What we're showing here is an example of doing a full optical mesh card where an MT connector from one of these slots can be fanned out with the 12 fibers to all of the other slots. So you can do a connection from any one slot to any one of the other 12 in full duplex transmit and receive from this direction to this direction. So the optics is opening up a very nice solution to solving the distance problems, improving the eye performance because of the challenges I mentioned, the electrical signal, and also giving some new flexibility in how this is all put together. So in summary, this is the view of the aperture system on the right side, the backplane apertures. And so in designing the backplane, you first start with what are the data requirements that I'm going to need to pass through the backplane. Is it a combination of electrical and optical? What speeds do I need to handle? And that is going to drive the optical transceiver and RF connections that are required. And once you know that configuration, you know what the backplane inserts. These are all of the inserts that are mounted on the backplane. And once you know all of these inserts, you know the faceplate and the apertures, the faceplate and apertures that will be required on the backplane system. So that's in summary of why the systems are moving to optical to solve these challenges. And again, VITA has been doing the driving force behind the standardization of these systems. All right, with that, I'm done.